Hi everyone, my name is Hailu Nigatu, and today I'll be talking about a 14-month cross-disciplinary co-design project during which we designed and implemented a document organization tool for practitioners working with police misconduct data. I'll give a bit of motivational background, and for that, I'm going to ask you to play pretend with me and imagine that you're a public defender, and you have a court case in a few days that involves a police officer testifying against your client. One thing that would help you in this case is if you had access to prior cases where the officer, let's call him Officer Smith, has, for instance, lied on the stand or committed another misconduct. In an ideal world, you would have access to well organized documents where you could just go to Officer Smith's folder, get the case files you need, and prepare your defense. But in reality, what you have is unorganized document dumps, which include semi structured folders, stray PDFs, images, audio files, etc. So you first have to find the case files before you can prepare your defense. So let's step out of the play pretend and delve into what's really in these types of document dumps. The first data challenge is that there's an overwhelming amount of documents. Secondly, there are full or partial exact copies of files with the same or different file names found across the document dump. Looking at individual PDFs, each page might come in different layouts such as narratives, forms, emails, handwritten documents, which all affect how you extract information such as officer names from each page. Fourth, there are legibility issues with different levels or types of redaction and different scan qualities of pages or physical alterations of pages which are otherwise identical. You also have files belonging to the same case, for instance, the department coming from the Department of Justice, the police department, and an external auditor, typically coming in scattered across several folders in the document dump hierarchy. And lastly, you have multiple case files blended in one large PDF with hundreds or thousands of pages, requiring you to first split up and find the individual case you're interested in before you can work on your defense. This type of data overloading is used as a strategy in the legal system. This is an article from the New York Times about how Abbott kept defense attorneys in discovery stage by sharing large amounts of folders for them to process in preparation for the defense. So it's not just public defenders, but defense attorneys, investigative journalists who are trying to hold institutions accountable, and as organizations such as the NACDL who work with such practitioners all deal with overloaded, messy data dumps. With these challenges, we saw that there was a clear need for data organization and cleaning tool for resource-constrained domain experts. We wanted to know how we can understand their needs and successfully build a tool for them. We approached this by having a computer scientist collaborate with data journalists, public defenders, and the NACDL in a cross-disciplinary collaborative team that underwent 14 months of a co-design project and built DOT, or a document organization tool, for domain experts working with police misconduct and use of force. In the rest of this talk, I will answer these 4 questions. And I will start with how did we co-design, and what did we find from our co-designing process? As a co-designing methodology, we used design by immersion, whereby I, the computer scientist, learned and enacted the manual data processing of the domain experts, and together with the domain experts, shared and discussed how to process the outputs, and based on our discussions, propose a tool, intervention, or solution for the problems that have been identified. And the domain experts helped me by identifying edge cases for the solutions that I propose, and I developed the tools with the same data sets that the domain experts use. Finally, they gave me feedback on design and implementation decisions, and we went through this process iteratively within our 14 months collaboration. The categories of findings from our co-design can be split into 2. The first is data needs, that is, what kinds of data tasks our users needed to do. And the second is the design goals that we set in order to match our users' priorities and workflows. Coming to the data needs, we found that our domain experts had 3 core tasks they needed to do in their data processing. That is data cleaning, data extraction, and data organization. And in fact, these 3 needs tackle exactly the 6 problems I presented at the beginning of the talk. The way I identified those challenges that were presented the start of the talk was through the co-design process. Coming to the design goals, our collaborative team set 5 design goals, and in this talk I'll focus on the 2, and I encourage you to read our paper for details about the other 3. So let's start with the first design goal, which is human control and intervention. The constraint we had for this were the fact that we were operating in a high-risk domain, and that through iteration, we found that domain experts preferred to be actively engaged in the decision-making process throughout the document organization task, rather than run the risk of having to come back after the fact to correct errors. The cost of an error is simply too high. A fully automatic solution just does not work for them. They need more control. And the implication of these constraints on our design is that our design should prioritize supporting our users instead of automating the whole process and replacing them. Coming to the second design goal that I'll discuss today is high-level abstractions. And for this, we observed that there was a trade-off in how flexible and useful a tool is versus how approachable or how plug-and-play it is. And since we wanted to go as far towards the flexible and usable end of the spectrum as we can, the way that we tried to find the right point on the spectrum is to understand how comfortable our users are with programming, and I'll give more details on this later on in the talk. So now I'll move on to answer what exactly did we build. Here's a snippet of a dot program a user has written, and it's using our classify and get per correlation abstraction. Under the hood, to implement just this one abstraction, we built on top of all the 4 building blocks that you see on the right. But our users do not need to understand these complex algorithms and techniques, and I'm also not going to ask you to understand any of them. Our abstraction design shields users from these difficult low-level implementation details. Here's the system diagram for dot as a whole. When users write a dot program, they're usually running their data through this general sequence. The input at the very start is a disorganized pile of documents, and the output at the end is a set of documents grouped according to the programmer's needs. You can see that all 6 of the core data needs are addressed, see the colorful icons, and the programmer gets to use the high-level dot abstractions instead of directly manipulating the low-level building blocks. Now I'll move on to answer what programming paradigms work for our users, and the reason that we asked this question is because through our collaboration, we found that some domain experts became self-taught programmers to automate some of their data organization tasks. So with this insight, we asked 2 research questions. Once we implemented the right abstractions, how do we best present it to our users? And 2, what are the relative strength of available programming paradigms for non-technical domain experts? So to answer these 2 research questions, on top of our Python library, we built 3 paradigm-specific interfaces and presented dot as a visual, programming by example, and traditional text-based interface. Coming to our results, for the first research question, surprisingly, we found that we could get participants up and running in any of the paradigms. Even text, which looked intimidating at first, by the 3rd task, participants were taking about the same amount of time with all 3 paradigms. It was all about getting them the right abstractions. In answering the second research question, we found that the text-based interface gave our participants low-level control and flexibility, such as importing outside libraries and functions. The visual paradigm allowed us to give them information such as histograms about their data, which they later used as they were writing their programs. And the programming by example put the focus on the examples that the participants were giving rather than the code that was being generated for them. And finally, I will reflect on what we learned from building dot. Here I'll highlight 2 of 4 reflection points from our co-design and encourage you to read the paper for more details. We found that our long-term engagement allowed us to build a trusting team and a shared vision. We also found that the collaborative design process allowed us to put prototypes into practice, sharing early-stage outputs and prototypes with the domain experts that they used in their workflows while we were still refining the design. With that, I will end my talk on the lessons we learned from a 14-month cross-disciplinary design team and leave you with 2 of the reflections from our project. Thank you.